Welcome to part 4 of our camera training series, image quality and camera reliability. A camera may have the right resolution and field of view, but its real performance is determined by how clearly and consistently it operates in actual field conditions. In this video, we will explore the factors that influence image usability, visual consistency, and dependable operation in demanding environments. By the end of this part, you will understand what makes a camera image truly reliable, not just in the laboratory, but in real-world missions. Let's begin. Welcome to part 4 of our camera training series, image quality and camera reliability. We begin with dynamic range, which determines how well a camera captures detail in bright sunlight and dark shadows within the same scene. Next, we examine noise performance, including how image noise and motion blur can reduce clarity, especially in low light or moving conditions. We will then compare different sensor types and understand when color or monochrome sensors are better suited for a mission. After that, we explore color reproduction, focusing on how accurately and consistently a camera displays colors under changing illumination. Finally, we cover durability, the camera's ability to withstand dust, water, temperature extremes, shock, and vibration in demanding environments. Let's begin. Dynamic range is a camera's ability to capture useful detail in both the brightest and darkest parts of the same scene. For example, imagine a vehicle moving through a dark tunnel toward bright sunlight. A camera with low dynamic range may show the outside as completely white, while the tunnel interior appears almost black. A camera with high dynamic range, often called HDR or WDR, preserves detail in both areas at the same time. The center image shows a camera with low dynamic range. The outdoor highlights become completely white, while important details inside the shadows are lost. On the right, a high dynamic range camera preserves information in both the bright sky and the dark tunnel. This produces a more balanced and usable image. Dynamic range is usually measured in decibels, or dB. A higher value generally means the camera can handle a greater difference between shadows and highlights. For vehicles, good dynamic range is important for sunlight, shadows, headlights, tunnel entrances, and rapidly changing lighting conditions. This image explains where a camera's dynamic range comes from. It begins with the CMOS sensor, which forms the foundation. Pixel capacity, read noise, pixel size, ADC bit depth, exposure, and gain determine how much brightness information the sensor can capture. Next, sensor HDR modes and the camera's ISP combine short and long exposures, apply tone mapping, reduce noise, and balance highlights and shadows. However, software cannot restore detail that the sensor never captured. Finally, real-world HDR or WDR depends on the complete camera system, including the lens, sensor, electronics, and image processing pipeline. So sensor creates the dynamic range foundation, but the complete camera determines the final usable HDR or WDR image. This image compares the published dynamic range capabilities of selected Sony and onsemi CMOS image sensors. On the Sony side, the IMX390 and IMX728 provide around 120 dB class HDR, while the IMX490 can reach up to 140 dB in dynamic range priority mode. On the onsemi side, the AR0233AT offers different values depending on the operating mode, from over 95 dB in single exposure to over 140 dB in multi-exposure HDR. The AR0820AT also supports up to 140 dB HDR, while the AR2020 family provides up to 100 dB in line interleaved HDR mode. The key point is that these figures depend on how the sensor is operated. For vehicles' navigation cameras, 120 dB is a strong practical target, while 140 dB class modes are useful for extreme backlighting and tunnel entry conditions. Low light sensitivity describes how well a camera can produce a usable image when very little light is available. This performance expressed using a lux rating. Lux is simply a measure of how much visible light falls on a scene. For example, bright sunlight can be around 100,000 lux. Indoor lighting may be around 100 lux, twilight is close to 1 lux, and a very dark night may be around 0.01 lux. A camera with a lower minimum lux rating can generally operate in darker conditions. So a camera rated at 0.01 lux should require less light than one rated at 0.1 lux. However, the rating only indicates minimum illumination. It does not automatically guarantee a clean, sharp, or noise-free image. A camera's lux rating is determined through a controlled, low-light test. First, a dimmable light source illuminates a test chart. A lux meter measures the amount of light falling on the scene while the camera observes the same target. The light level is then gradually reduced until the camera reaches the minimum level at which it can still produce a usable image. The result may appear in the datasheet as 0.01 lux f1.2, 1 by 32nd ATC on. Here, 0.01 lux is the scene illumination. f1.2 is the lens aperture, 1 by 32nd is the exposure time, and AGC on means electronic gain was enabled. AGC stands for Automatic Gain Control. In a camera, AGC automatically increases the electronic amplification of the sensor signal when the scene becomes dark. Therefore, the lux rating describes the complete camera system under stated test conditions. We have now completed our discussion on dynamic range and how cameras manage bright highlights, dark shadows, and challenging lighting conditions. Let us move to the next topic, noise performance. Here, we will understand how signal-to-noise ratio, image noise, and motion blur influence clarity and the usability of video from a vehicle camera. Image noise is the unwanted random variation that appears in a camera image, even though it was not present in the real scene. It may look like grain, colored speckles, horizontal bands, flickering, or isolated bright pixels. Noise becomes more visible when the camera receives a weak signal, especially in low light. Common causes include high gain or AGC, small pixels, sensor heat, short exposure times, and electronic readout noise. There are several types of image noise. Luminance noise appears as random brightness grain. Chroma noise creates colored spots. Fixed pattern noise appears as repeating lines or bands, while hot pixels show up as isolated bright dots. For a vehicle camera, excessive noise can hide obstacles, road edges, wires, people, and distant objects. So image noise is not used for scene detail. It is an unwanted artifact that reduces image clarity and overall camera usability. Signal-to-noise ratio, or SNR, compares the useful image information captured by the camera with the unwanted noise present in the image. The signal is the real scene detail, such as obstacles, road edges, people, vehicles, and terrain features. The noise is the unwanted grain, flicker, colored speckles, or random variation that reduces clarity. SNR is usually expressed in decibels, or dB. A higher SNR means the useful signal is much stronger than the noise, producing a cleaner and more usable image. When noise becomes too strong, important scene information becomes harder to detect. This is especially critical for vehicle navigation in low light and difficult operating conditions. Now let us compare high SNR and low SNR. In the high SNR image, the road, rocks, vehicle, and terrain edges remain clear because the useful signal is much stronger than the noise. In the low SNR image, heavy grain hides distant terrain and makes obstacles and edges harder to detect. Typical SNR values help us judge image quality. Below 20 dB is usually very noisy. Between 20 and dB, noise remains noticeable. Around 30 to 40 dB generally provides good image quality, while values above 40 dB can produce a clean image under suitable conditions. For UGVs, higher SNR improves obstacle detection, terrain visibility, and reliable navigation. We have now completed noise performance and understood how noise, signal quality, and motion blur can affect image clarity. Let us now move to sensor types. In this section, we will look at color and monochrome sensors and understand how the right sensor choice depends on lighting conditions and the vehicle's mission requirements. Sensor type and spectral capability together determine what a camera can see and how it represents the scene. Sensor type refers to how the sensor captures and presents light. A color sensor produces natural RGB images, while a monochrome sensor offers higher sensitivity and stronger low-light performance. Thermal sensors detect heat, and multispectral sensors capture selected wavelength bands for specialized analysis. Spectral capability refers to the range of light or radiation the sensor can detect, such as visible light, near-infrared, MWIR, or LWIR. For UGV applications, choosing the correct sensor type depends on the mission, daylight navigation, low-light operation, thermal detection, or material and vegetation analysis. Here we explain spectral capability, the range of wavelengths a camera can detect. Visible light cameras typically operate between about 400 and 700 nanometers. Many silicon CMOS sensors can also detect near-infrared light from roughly 700 to 1000 nanometers. Thermal cameras use different detector technologies for MWIR and LWIR wavelengths. Color cameras often use an IR cut filter for accurate daytime color, while day and night cameras may remove this filter in darkness. Monochrome sensors usually respond better to NIR. For vehicles, this directly affects mission suitability. Color CMOS supports daytime navigation, monochrome or day-night sensors support low-light operation, NIR-sensitive cameras enable assisted night driving, and thermal or multispectral sensors support detection and specialized analysis. We have now completed our discussion on sensor types and understood the differences between color and monochrome sensors. Let us now move to color reproduction. In this section, we will explore how cameras maintain accurate and consistent colors under sunlight, shadows, artificial lighting, and changing illumination conditions. White balance is the camera's method of correcting the overall color cast of a scene so that white objects appear truly white and other colors look natural. Different light sources have different color characteristics. Tungsten lighting may make the image look yellow or orange, shade can make it appear blue, and fluorescent lighting may introduce a green tint. The camera corrects this by adjusting the red, green, and blue channels through its image processing system, or ISP. This is important because the same white object can look very different under changing illumination. Without white balance, a white surface may appear warm, cool, or greenish depending on the light source. So white balance helps the camera compensate for lighting color and maintain a more neutral and realistic image. The first image shows the difference before and after white balance correction. Before correction, the scene may have a strong yellow, blue, or green color cast. White objects no longer look white, and other colors also appear unnatural. After white balance, the camera adjusts the red, green, and blue channel gains. This removes the color cast, restores neutral whites, and makes the overall image look more realistic. The image on the right explains auto white balance, or AWB, in real operation. As a vehicle moves from sunlight into shade, indoors, or under street lighting, the camera continuously estimates the illumination and adjusts the colors automatically. Good AWB helps maintain natural and consistent color. Poor tuning, however, can cause visible color shifts or sudden changes between video frames. Color accuracy describes how closely the colors in a camera image match the real colors of the scene. A red warning sign should look red, green vegetation should remain green, and white or gray objects should stay neutral. This is important because color is often used for identification, interpretation, and decision-making. Good white balance helps remove the overall color cast, but it does not automatically guarantee accurate individual colors. The sensor, filters, lens, and image processing system must all be correctly calibrated. Color accuracy matters because incorrect colors can cause confusion. A warning sign may be misread, Vegetation may appear unhealthy, soil and rocks may be classified incorrectly, and vehicle markings or equipment status may become difficult to identify. For vehicle operations, accurate color supports reliable viewing, terrain assessment, object recognition, and operator judgment. In the accurate image, vegetation looks natural, the road surface remains neutral, and the vehicle's colors and markings are easy to identify. In the inaccurate image, the scene has a strong color shift. Vegetation appears unnatural, the road tone is distorted, and objects become less reliable to interpret. The image on the right shows that color accuracy depends on the complete camera system. The sensor's spectral response, Bayer filters, IR cut filter, white balance, lens transmission, lighting spectrum, and ISP color correction settings all influence the final result. Even the display and video encoding can affect what the operator sees. So good color accuracy requires proper sensor selection, calibration, and careful tuning of the full imaging pipeline. Color consistency under changing illumination means that the same object should continue to appear approximately the same color, even when the lighting around it changes. For example, a green vehicle should remain recognizably green in bright sunlight, deep shade, indoor lighting, or under night street lights. Good color consistency reduces sudden color shifts and helps both the operator and AI system trust what they are seeing. This is difficult because different light sources have different color characteristics. Sunlight may appear neutral or slightly warm, shade often looks bluish, indoor lighting can look yellow, and streetlights may create a strong orange cast. Without proper processing, the same white or green object can appear very different under each condition. The camera must therefore continuously compensate for the changing illumination. We have now completed color reproduction and understood how cameras maintain accurate and consistent colors under changing lighting conditions. Let us now move to the final topic, durability. Here we will examine how cameras withstand dust, water, temperature extremes, shock, and vibration during demanding virtual operations. An IP rating, or ingress protection rating, tells us how well a camera enclosure is protected against dust and water. The rating is written using 2 digits. In IP67, the first digit, 6, refers to protection against solid particles. A rating of 6 means the enclosure is dust-tight, so harmful dust should not enter during the specified test. The second digit refers to water protection. A rating of 7 means the camera is protected against temporary immersion in water. A rating of 8 indicates protection against greater immersion, but the exact depth and duration must be stated by the manufacturer. So, IP67 and IP68 describe enclosure protection only. Here we compare IP67 and IP68. Both ratings provide complete dust protection, the 6th part is the same. The difference is in water resistance. IP67 generally protects the camera against temporary immersion, commonly up to 1 meter for around 30 minutes. IP68 provides protection for deeper or longer immersion, but the exact depth and duration must be confirmed from the manufacturer, commonly around 1 to 3 meters for 30 to 60 minutes. The image on the right explains why this matters for vehicle cameras. These cameras may face dust, rain, mud splashes, and shallow water crossings during operation. For exposed vehicle cameras, IP67 is a practical minimum, while IP68 is preferred where greater water exposure is expected. This image explains how to read an IP rating, or ingress protection rating, and what each digit means. The first digit represents protection against solid objects and dust. A rating of 1 blocks objects larger than 50 millimeters, while ratings 2, 3, and 4 protect against progressively smaller objects down to 1 millimeter. A rating of 5 means limited dust may enter, but not enough to affect operation. A rating of 6 means the enclosure is completely dust-tight. The second digit represents water protection. Ratings 1 and 2 cover dripping water, while 3 and 4 protect against spray and splashing. Rating 5 covers low-pressure water jets, and rating 6 covers stronger water jets. For immersion, IPX7 generally means temporary immersion up to 1 meter for about 30 minutes. IPX8 means immersion beyond IPX7 conditions, with the exact depth and duration specified by the manufacturer, commonly around 1 to 3 meters for 30 to 60 minutes. So IP67 means dust type plus temporary immersion protection, while IP68 means dust type plus greater immersion protection. This image explains the process of converting a standard market camera into an IP67 or IP68 rated rugged camera suitable for demanding outdoor applications. On the left, we begin with a normal commercial camera. It may perform well optically, but mechanically it can have several vulnerable ingress points. These include the housing split line, the lens barrier interface, the rear cable or connector entry, and the screw holes. If these areas are not properly sealed, dust, rainwater, mud, or moisture can enter the enclosure. The absence of pressure equalization can also create internal pressure differences that may draw water through weak seals. The middle section shows the engineering modifications required. First, a continuous perimeter gasket or O-ring is added between the housing parts. This creates the primary barrier against dust and water. A tongue and groove or labyrinth joint can also be introduced to make the water path longer and more difficult. The lens barrel is then sealed with an O-ring or protected behind a sealed optical window. At the rear, the cable exit should use an IP-rated connector, cable gland, overmolded cable, or potted exit. Fastener holes must also be controlled using blind threaded holes, sealing washers, or O-rings beneath screw heads. A hydrophobic EPTFE vent can equalize internal pressure while preventing liquid water from entering. The housing itself must have flat sealing surfaces, correct gasket compression, proper screw spacing, specified tightening torque, and corrosion-resistant hardware. Finally, the complete assembled camera must be tested for dust and water ingress. The result is the ruggedized camera shown on the right, sealed, pressure-balanced, mechanically robust, and ready for IP67 or IP68 validation in harsh operating environments. This image summarizes the key design practices needed to build a reliable IP67 or IP68 enclosure. First, the gasket must be compressed within the correct range, typically around 15 to 30%. Too little compression can cause leakage, while too much can damage the seal. Screws should be evenly spaced and tightened in a cross pattern so the cover does not distort. The sealing faces must also be flat, smooth, and free from scratches or burrs. Compression stops help prevent over-tightening, while correct torque ensures uniform pressure across the gasket. The seal should remain serviceable, allowing inspection and replacement without damaging the housing. Corrosion-resistant fasteners, such as coated or 316 stainless steel hardware, improve durability. Finally, the enclosure should avoid water traps by using sloped surfaces, drainage paths, and good external geometry. Reliable IP protection comes from good design, correct materials, controlled assembly, and proper validation testing. Now let's look at another environment factor: temperature. The operating temperature range defines the ambient temperatures within which a camera can start, operate continuously, and maintain acceptable performance. This range is determined by the complete camera system, including the CMOS sensor, processor, power electronics, memory, connectors, PCB, seals, and housing materials. The component with the lowest temperature capability can limit the entire camera. Internal temperature is usually higher than ambient because the sensor, processor, and regulators generate heat. The enclosure must therefore conduct this heat away using aluminium housing, thermal pads, or cooling fins. At low temperatures, cameras may face startup failure, stiff seals, condensation, and focus changes. At high temperatures, noise, hot pixels, thermal shutdown, and component aging may increase. Finally, the specified temperate range must be verified through cold start, high temperature operation, thermal cycling, image quality, and sealing tests. Now let's look at another durability factor for a camera: shock resistance. Shock resistance describes a camera's ability to survive sudden impacts without cracking, losing video, damaging electronics, shifting the lens, or breaking its environmental seal. It is normally specified using three parameters: peak acceleration in gear, pulse duration in milliseconds, and the shape of the shock pulse, such as a half-sine wave. For example, a requirement may state 50G for 11 milliseconds across all three axes. The image also shows that shock travels through a complete load path from the vehicle and mounting bracket through the enclosure, PCB, optics, and internal components. The weakest part can limit the entire system. Shock resistance can be improved with a rigid metal housing, strong mounting brackets, controlled isolation, secured PCBs and components, locked lenses and connectors, and proper validation testing. Let's look at one last durability factor for a camera: vibration resistance. Vibration resistance describes how well a camera and its enclosure continue operating under repeated mechanical movement. Unlike shock, which is a sudden impact, vibration acts continuously over time. For a vehicle camera, this may come from rough terrain, wheels, tracks, motors, or the mounting structure. Vibration is specified using the frequency range, vibration amplitude or acceleration, random vibration levels such as PSD and GRMS, test duration, and all three axes. The image also shows the vibration load path from the vehicle through the mounting bracket and enclosure into the PCB, optics, connectors, and components. The weakest or most flexible part can limit the whole system. Resistance can be improved using a rigid housing, strong bracket, resonance control, carefully selected isolators, secured electronics, and locked lenses and connectors.
This brings us to the end of Part 4, Image Quality and Camera Reliability. In this video, we explored dynamic range, understood noise performance, compared different sensor types, examined color reproduction, and reviewed the importance of camera durability in demanding environments. Together, these factors determine whether a camera can produce clear, consistent, and reliable imagery during real-world operations. In Part 5, we will move on to camera integration and understand how cameras are connected, configured, synchronized, calibrated, and deployed on a vehicle. I hope you found this video useful and informative. Thank you for watching, and I look forward to seeing you in Part 5.